more complex number stuff. This is de Moivre's theorem. Now, if z equals cosine theta plus I sine theta, then for any n contained in z, z to the n equals cosine theta I sine theta to the power n, which equals cosine n theta plus I sine n theta. This is de Moivre's theorem. Now, here's an example. When n equals 0, sorry, it's just equal 1. And we all know that as basic trigonometry, cosine theta plus sine theta, I sine theta. Now, and cosine 0 multiplied by theta plus I sine 0 multiplied by theta equals cosine of 0, I sine of 0 equals 1. Just plug in some numbers here, because n is here, there, this part, and then we're distributing this n into these values here, so as we have done here. So this shows that it's working for n equals 0, but that's obviously not good enough. In mathematics we need to do it for all problems, otherwise it's not a theorem. It's just a conjecture where it's not being proven. It's not even a conjecture. But anyway, as an example for n equals minus m, where m is a positive integer, then cosine the theta plus I sine theta to the n equals cosine theta plus I sine theta to the negative m, which equals 1 over cosine theta plus I sine theta to the m. Now, we know that by de Moivre's theorem this to be true. Now, since m is a positive integer, so cosine theta plus I sine theta to the n equals 1 over this. We're plugging in the m values for de Moivre's. So once these have been plugged in, we'll get, because this we can think of as to the negative 1, like all this quantity to the negative 1 as well. So by de Moivre's theorem, we'll get cosine minus m theta plus I sine minus m theta, which in turn equals cosine n theta plus I sine n theta. Now, here's an example. Now, show z cubed equals minus 27 in polar coordinates in terms of r and theta. Then write the solution in Cartesian. Now, we'll let z equals r cosine theta plus I sine theta. Also, minus 27 equals 27 cosine pi plus I sine pi. So equation, this equation z to the 327 is r cubed, cosine theta plus I sine theta cubed equals 27 cosine pi I sine pi. So using de Moivre's theorem to find a polar term of the left hand side, we get this, plugging in the powers, the third powers, which equals 27 cosine pi plus I sine pi, which gives us r cubed equals 27, so r equals 3. Now, the solution for any k contained in z, the integers, 30 equals pi plus 2k pi, which rearranging gives us theta equals pi over 3 plus 2k pi over 3, where k equals 1, 2, 3, and so on. So theta equals pi over 3, pi, 5 pi over 3, and so on. So we'll just use these three values just to show. So z0 equals 3 cosine pi over 3 plus I sine pi over 3, and z1 equals 3 cosine pi plus I sine pi over 3, and z3 equals 3 cosine 5 pi over 3 plus I sine 5 pi over 3. We write z2 using its principal argument. And z2 equals 3 cosine minus pi over 3 plus I sine minus pi over 3. So in Cartesian, we're just plugging in these values. We get z1 equals minus 3, z2 equals this. And z0, these are the directions on the complex plane here. These are just reflections of one another. And this is where z1 equals negative 3. Because it doesn't really have any other components other than negative 3. So this is z1. So it should all be pretty easy to see where all these plug in. and so on. Now the roots of complex numbers, let a equals rho cosine phi plus I sine phi be a complex number in polar form. Then for any n contained in n, the natural numbers, the equation z to the n equals a has the solution z equals rho to the 1 over n cosine, and then we're plugging all these in what we derived above for our theta value for k equals 0, 1, dot dot dot, any n to the n minus 1. Now the fundamental theorem of algebra: every polynomial equation a n z n z to the n, a n minus 1, z to the n minus 1, and so on equals 0, where a n minus 1 and a naught is contained in the complex numbers, where a n does not equal 0, has at least one solution in the complex number system. That's the fundamental theorem of algebra. Now the factor theorem: let p of z be a polynomial with coefficients in the complex numbers, and let alpha be contained in complex numbers, then p of alpha equals 0 in if and only if z equals minus alpha is a factor of pz. Now where every polynomial p of z equals a n z to the n plus a n minus 1 z to the n minus 1 plus dot 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 plus a1 z plus a naught, where n is greater or equals to 1 and coefficients are contained in a complex number with a n does not equal 0, can be factorized as this in this form, where complex numbers a1, a2 to an are roots of our polynomial p of z. Now in exponential form we get this, and we'll keep going on, z2, z3 or whatever, just to get the idea here. So that was complex numbers. Thanks for watching, and please do subscribe.